Okay. First, I must apologize up front. My voice is not very good these days. Hopefully it'll hold out through the whole thing. But since this is an invited talk, I decided to do something rather different. So if you're expecting a talk on Sigma, this is not that. Instead, it's kind of an overview of the analytical side of my career that complements the synthetic side that include creating cognitive architectures such as SOAR and Sigma. Oops, there's the actual title slide. So we're going to look at a hierarchy of three analyses, starting with sorry, something's not quite going right. But it's going to be a bit of a whirlwind. We're going to go through three in the time I have available. So in a time of global warming, you should expect a whirlwind. So the plan of the talk is we're going to start with the highest level at understanding computing as what I call a great scientific domain, which will highlight the role of information, which is the broader conference here, as well as the intradomain nature of AI cognitive modeling and BICA in particular. We're then going to look at an approach to mapping essentially the underlying technologies in AI, cognitive modeling, and cognitive architectures in particular via a quartet of dichotomies. And through that, we're going to highlight the scope, similarities, and differences among these technologies. The third level then is a common model of cognition, which based on a partial consensus across cognitive architectures. And then just a bit of analyzing a particular cognitive architecture, the Sigma architecture, based on the second and third levels. And I'm going to swap the second and third in order, just because I'm going to use examples from the third in going over the second. Okay, so here's understanding computing. And it's going to be done in the context of essentially the physical life and social sciences. Here, computing is denoted by a Turing machine, and there are images that are characteristic of the other three domains as well. So we're going to focus on computing in large. So that means computer science and engineering, information science and technology, computational science, informatics, all of those kinds of things. It's not just computer science. And also science and engineering, academic industrial aspects, unidisciplinary and multidisciplinary aspects. So it's this broad notion of a domain of computing. And then we're going to understand that as what's called a great scientific domain that in particular is concerned with information and its transformation. So this is where the notion of information becomes central. So a great scientific domain is a concept that arose out of reflecting on the three pre-existing domains. And there's different ways to conceive of these, but roughly the physical life and social sciences. Everyone kind of is familiar with these notions, but there's no common understanding for what makes these great scientific domains, and what it would mean for anything else to be in that same category. So in reflecting on those and on what computer science or computing in general, I came up with a definition, which is basically the understanding and shaping, that's in some sense the combination of science and engineering, of a significant body of distinct interactions among structures and processes. So it's those interactions among structures, processes that is key, both natural and artificial. So we're not making a strong distinction between those two spheres. So computing then concerns informational structures and transformational processes in the interactions between those. Once we have the notion of great scientific domains, we can start to look at them and the relationships among them in terms of this relational approach. So what we're doing is we're understanding domains in terms of their cores, as well as the domain-domain relationships, including relationships with themselves. So the core is the pure region. For these three, it's like physics versus biology versus psychology. But much of the exciting overlap and important work is in the overlaps. And so here we're going to use the initials to represent the domains and just a plus to represent a general notion of overlap or relationship. So if we're doing physical and social, it's things like human-induced global warming. Physical in life, you get things like molecular biology and genomics. Social in life, you get cognitive neuroscience. You put all three together, you get things like ecology and consilience. If you combine that with computing as the fourth domain, you get a tetrahedron of the four domains rather than a triangle of three. And the monadic or pure portion is things like theory, algorithms, and languages. We can look at a dyadic portion that includes computing plus one other domain, generically notated by delta. But then if you look at computing combined with each of the other four domains, including itself, combining it with the physical domain, you get some very different kinds of things, everything from robotics to computational chemistry to digital physics. Combining with life, you get DNA computing, computational biology, bioinformatics, and other things. With social, that's where AI comes in, and cognitive modeling, human-computer interaction, social networks, a variety of kinds of things. And if you combine computing with itself, that's networking, operating systems, compilers, and so forth. And then if you go beyond that to polyadic, where you combine more than two domains, you start to get some very interesting and futuristic topics like prosthetics, intelligent robots, mixed reality, and in fact, BICA, which we'll talk about a little more in a few minutes. So given this notion of relationship among domains, we can then go down another level below that by looking at specifically two different types of relationships between domains, implementation and interaction. So implementation has one domain bringing into effect another domain, shown by this kind of divisional slash. So silicon electronics, for example, can implement a computer. An interpreter uses one language to implement another. AI implements aspects of people on computers. So you get to different forms of implementation in each of those. Interaction focuses on influence in possibly different directions between domains. So human-computer interaction differs from AI in being an interaction between S and C rather than an implementation relationship between them. Computer networks is a relationship or interaction among multiple computers, and you can use a variant of the Kleene star, which basically says two or more instances of those influencing each other. And then you can go beyond that to things like physical sensor networks, where the physical world is influencing a computer, and then you have interactions among many of those. One of the things that got me most excited about this relational approach early on was that if you just look at dyadic computing, so computing combined with one other domain, and then look at that crossed with the different kinds of relationships, you can get a map of much of modern computing in a very structured fashion. So instead of a long list of topics, here you can begin to get an idea of how computing actually breaks up in this kind of a fashion. If you then look, for example, at AI and cognitive modeling, you can see that both of them are basically the social implemented by computing. But if you want to dig a little further into something like cognitive modeling, you can say it's that social implementation, a computing implementation of the social that's influenced by the social. That is, you're referencing people and understanding how to build social on top of computing. Neural networks in the simplest form are just an implementation of life on top of computing, but you can also think of it more generally as implementing social or thought on top of life on top of computing. If we go to BICA or BICA then, it's a triadic discipline involving computing, life, and social, so it's down in the intersection of those three. The simplest way of representing it is as S L over C, though there are other forms, some of them more complicated, some of them simpler in various ways. So this kind of situates BICA in terms of the larger world of science and engineering, essentially. Okay, let's go on to the next step, which is going to be the third level. As I said, I'm going to do that before the second level. And this is the notion of a common model of cognition that's over both kind of human and artificial minds. So you can see here kind of a relational approach to thinking about it, reflecting the fact that we have a model here that includes both human or natural and artificial intelligence, though the arrows here have to do with these relationships rather than a modeling or abstraction relationship. So we're going to start with the notion of a mind as a functional entity that yields intelligent behavior. Minds are studied from multiple perspectives: AI, cognitive science, neuroscience, robotics, AGI, if you think of it as something different from AI, and other kinds of fields as well. There's a deep scientific question, though, as to whether they will converge on a single understanding of mind. We can think of that as a single peak, or whether there are many different peaks that the different fields will yield. What we do know is that it must at least happen for cognitive science and neuroscience, since they're studying the same object, what we call the brain-mind combination. For biologically inspired AI, it might also fit if the class is slightly abstracted. So it's not just the human mind and brain, but includes related forms of biologically inspired minds. And so also may other work that is similar for functional reasons, that isn't necessarily the human mind and brain, or directly inspired by it, but ends up being essentially in the same peak for other reasons. Something weird is going on here. So we're going to call this slightly abstracted class human-like minds. It's broader than naturally inspired minds, includes natural minds, for example, but narrower than human-level intelligence. Okay, then when we get to the common model of cognition, what we're trying to go for is a community consensus on what must be in particular a human-like cognitive architecture. So cognitive architecture, again, is a hypothesis about the fixed structures and processes that underlie a mind. So it includes ability to store information and reason about it and learn, use language, all of those kinds of things. The common model, though, is abstract and not itself a cognitive architecture. Potentially yields a range of benefits, including the coherent baseline to facilitate shared cumulative progress, provides a target for challenging the consensus, a way of organizing the data need for evaluating cognitive architectures, and an interlingua for comparing architectures if they're all mapped onto this common model. And also guidance in adding components to existing integrated systems of various sorts, or if you have a neural network model and want to add memory, for example, guidance in identifying relevant experiments to understanding, for example, which cognitive architectures might be more appropriate as models of the human mind or other things, and in developing applications. So the structure of the common model is in some sense fairly simple at this point. It's a small set of communicating modules. It includes long-term memories, procedural for skills, declarative for facts, a short-term working memory, plus perception and motor modules, and they're all interconnected in particular ways. There's global communication through the working memory, plus a local perception motor link. Procedural long-term memory can access all of working memory. The other modules can only access a small buffer within working memory. Plus, there's 16 additional assumptions, at least in the initial form of the model, such as that there's a lot of parallelism, both within and across modules. There's a sequential cognitive decision cycle that runs at about 50 milliseconds in humans, and that the system is pervasively hybrid in terms of combining symbolic data and quantitative metadata about the data. So here are kind of conventional diagrams and descriptions for three particular cognitive architectures that heavily influence the initial versions of the common model. But they're color-coded essentially according to the common model diagram, so you can see what portions of each correspond to the common model. You can see that all three are rather different. In Pei's terms, the first two, Actar and SOAR, are essentially integrated models. Sigma is a unified model of a sort. It's essentially all one large extended graphical model or factor graph, where the different functionalities come about by specialization and combination across those areas. Now, if we try to analyze these three architectures in terms of the common model, what we see is that a couple of decades ago, SOAR and Actar differed from the common model in a number of ways, highlighted by the red squares, divided up into four different kinds of topics in which we looked at the common model. They not only differ from the common model, they differed from each other. So you can see the red squares in different places. But if you look at them now, they're essentially in complete agreement with the consensus, although they're not completely implemented. That's what some of the later green things to note. Sigma is different. It's both newer, so it's less completely implemented. And there are a number of things that are implemented architecturally in these other systems and in the common model effectively, which are implemented essentially on top of the architecture through knowledge and skills in Sigma. So one of the most interesting developments since the development of the early notion of the common model, and one that was unanticipated at that time, was the notion of the common model as a large-scale brain architecture. So not just an architecture of the mind, the cognitive level as viewed in AI, but the brain as viewed in neuroscience and cognitive neuroscience. This starts by mapping the common model onto the brain, and particularly onto various kinds of neural circuitry. There's a fairly standard way to do this. You can find a form of it in ACT-R and in other kinds of ways, but it happens in a particular way for the common model. We can then use that mapping to compare the common model to more standard large-scale brain architectures from the neurosciences, including variants on hub and spoke architectures, which have a central component and others attached to it, as well as hierarchical architectures, which start at a bottom level and build up to a root of a tree of components, essentially. And then the key result here is that if you look at a technique called dynamic causal modeling and apply that to data for 6 tasks from the Human Connectome project, you'll see that if you look at the pink Gaussian in each of the top 6 figures, it's to the right of all the other Gaussians, which means the common model is actually doing a better job at modeling the data from all 6 of these tasks than are the traditional neuroscience models. And if you look at G, which is all tasks combined, you'll see that basically there's a 100% probability, or a probability of 1, that the common model is a better model than all of these other models. So that was kind of a surprise and really a nice kind of extension of the common model. There's other kind of work with the common model as well, which I don't have time to go into at this point, but that one's kind of the most important, most interesting one. So concluding on the common model, it reflects a very real initial consensus, particular modules and connections, serial and parallel processing, symbolic and sub-symbolic representations, procedural and declarative memories, and pervasive learning as a side effect of performance. This is a slightly different notion than Pei's notion of learning as reasoning, though I think there are ways to bring those kinds of notions together. It shows promise as a large-scale architecture of the brain, but remains incomplete in a number of ways. There's no metacognitive or reflective capability in it, no emotion or mental imagery, no social cognition, theory of mind, things like that. So those are ways that the common model needs to be extended. And it may still be wrong in various ways. That's still to be determined by challenges. And the hope is that it yields a sound beginning, though, upon which to build. There's a community now, includes a mailing list for the community, and kind of an archival list of publications in a journal form. You can see both of those here. Okay, now let's go to the third major topic, pulling back up to the second level. And we're going to talk about creating maps of AI and cognitive modeling, cognitive architectures. Again, you can see kind of the expressions in the rational approach for it. But in this case, focused on the technologies that underlie the core aspects of particularly memory, processing, and learning. So we're not looking more broadly at natural language, emotions, and so on, except for how they derive from these kinds of core capabilities. Much of this work is still in preliminary form, so don't be surprised if it changes before it's published. Some of it's published in conference papers, but I'm working on a large 80-page paper on the overall thing at this point. Okay, so here's kind of where we start. These are the underlying technologies that are covered in this work. You can see it's a fairly large list, organized by, in some sense, a mishmash of non-orthogonal categories, which then include modifiers and variants to provide a fairly succinct way of listing of wide range of technologies that you find across AI and cognitive science. Hopefully you see many of your favorites here. I'm not going to give you time to really look at them in great detail. Unfortunately, this chart doesn't say much more about the individual technologies other than sort of category and modifier / variant, if any. So the goals of this work are to progress from such a coarse and ad hoc categorization of technologies to n-dimensional maps that cover those fields and that reflect the inherent structure underlying them. And then to begin to use these maps to understand the scope of technologies across AI and cognitive science, to understand these technologies in terms of the space's structure, similarities and difference among them in some detail, and eventually trade-offs among them, but I don't really focus on that in this talk. For some reason, it's sometimes not moving ahead and sometimes moving ahead too. Must be a Zoom PowerPoint interaction because it doesn't happen normally. But okay, and then understand the rationales for particular integrations in cognitive architectures. Based on the need to span dichotomies, this is part of what's in integration, and in fact, the underlying criteria, but again, that's not something we'll focus a lot on in this talk. Okay, so there are 4 dichotomies that I'm used to structure the overall space. Each of them is essentially, can be viewed as a centroid of a larger space of dichotomies. We'll see how that works as we go forward. The first one is what I call asymmetric. It's whether processing proceeds uniformly in all directions or in a single direction. So you can think of logic versus rules. In rules, you can infer in both directions, forward and backward, but it's a different kind of inference. It's abduction versus deduction in backward versus forward. So rules are asymmetric, whereas logic can get deduction in any direction. Inconsistent, whether processing considers a single consistent situation or multiple inconsistent situations. So here you can think of monotonic versus non-monotonic logic as an example. Metadating, whether processing focuses on symbolic data or numeric metadata. This is kind of in a common model way of thinking about things. So here we get rules versus neural networks, for example. And then there's non-combinatoric, whether processing complexity is exponentially greater or sub-exponential. So here we can think about, for example, planning versus the use of policies. Now, these 4 dichotomies weren't just plucked from thin air. The first 2 actually came out of an attempt to understand the structure of cognitive architectures and the common model in terms of the cross product of those 2 dichotomies. So we can see, for example, procedural and declarative memory as consistent, but differing in terms of whether they're asymmetric or symmetric. Cognitive cycle then shows up as an inconsistent asymmetric thing. It's constantly changing between individual situations. And the common model does not have an inconsistent symmetric component. If you look at SOAR, it refines those consistent things to parallel rules for declarative memory, procedural memory, facts and episodes for symmetric declarative memory. It has the cognitive cycle. It adds a form of reflective subgoaling for the inconsistent symmetric component. And then you can do this with more kinds of cognitive architectures as well. The bottom 2, and again, the first one, were used in an attempt to understand the traditional but coarse-grained dichotomy between symbolic and subsymbolic approaches. Here we have essentially a map that involves all 3 of these dichotomies, and symbolic versus subsymbolic are opposite corners of a cube that results, just shown here as 2 different planes. So it shows essentially that symbolic is combinatoric symmetric data processing, whereas subsymbolic is non-combinatoric asymmetric metadata processing. But this chart or map actually shows more than that. It contains, does not want to progress. It's now frozen. Right, now it's going again. The map also shows many intermediate forms, each of which shares one or more traits with each of the two extremes. So it's not just symbolic versus sub-symbolic in this analysis. It's a much broader space of possibilities. And in fact, you can get transition paths between the two extremes. So for example, you can go from first order logic to rules, down to arithmetic circuits, over to feed-forward neural networks. Or you can go from something like statistical relational AI to probabilistic graphical models, to Boltzmann networks, to recursive neural networks. So those go by switching values on one dichotomy at a time. Okay, if we now look at those four dichotomies in turn, this is the asymmetric one, and we've looked at rules versus logic, but you can see there's a large space of dichotomies across many different subfields, which can roughly be categorized as asymmetric versus symmetric. If we look at just two of them, heteroassociative versus autoassociative networks, that's basically feed-forward networks versus Boltzmann machines, and procedural versus declarative memory, as in the common model. Now, this is just a for example at this point, and I won't make much more about it, but this is an example of what you can try to do in identifying the criteria that determine why you'd want to be at one end of a dichotomy or the other. So for example, asymmetric seems to prefer or help with precision and combinatoric efficiency, whereas symmetric helps more with correctness, robustness, and problem generality. And you can start using those kinds of criteria to understand when you want one versus the other, or in fact, both. Here's inconsistent, and we looked at monotonic versus non-monotonic logic. Another interesting one here is backpropagation versus reinforcement learning. They're both asymmetric, but they differ in consistency. And if you try to span this dichotomy by including both, you get things like deep reinforcement learning. If you combine the two dimensions, take the cross product of them, you get essentially four generic capabilities: reaction, reasoning, deliberation, and reflection across the four cells. You can view this as a way of understanding cognitive architectures where you have memory and control, and two kinds of each, depending on whether they're consistent or, asymmetric or symmetric. You can also view this as a way of looking at things like 3T architectures in robotics, where you get an L-shaped version going from reaction to deliberation to reflection. You can further fill out these cells then with all of the different types of technologies that classify according to these two dimensions. And you can go beyond this to say, okay, if I want to build a cognitive architecture that has these four capabilities, I'm free to pick one technology from each of these four cells. Now, there may be better or worse ways of doing that, but in some sense, you're free to do that in general. Okay, here's metadata versus data. And again, there are various versions of that. You can then combine that with the other two in an abstract form, and you can add a row for spanning, which gives you these hybrid things. You probably don't want one technology for each of these 12, because generally you'll want only one from metadata data or spanning, but then also you want the other kinds of alternatives. Here, the original analysis of sub-symbolic versus symbolic basically reduces to quantitative reaction versus qualitative reasoning, although you can extend that by shifting from qualitative reasoning to qualitative reflection, which gives a slightly more extreme version of that same coarse dichotomy. Interestingly, though, if you just shift that latter one down to hybrid reflection, you get the architecture of AlphaZero, which comes more out of the machine learning tradition, but includes feed-forward networks as well as Monte Carlo tree search. If you move all of them to the hybrid row, you get a way of looking at the SOAR and Sigma architectures, which each have variants on each of these four cells. If you then drop hybrid reflection, you get the common model and ACT-R, neither of which have explicit reflective components at this point. And then, of course, you can flesh all of those out. Here's the fourth one, non-combinatoric versus combinatoric. And again, a range, though there are a smaller number of existing dichotomies that seem to fit into this particular cluster, essentially. I'm not going to show you a four-dimensional table with all of the technologies. That's not terribly useful. What I want to do is just quickly show how you might use this to understand a particular architecture in a bit more detail. So this is how Sigma in particular spans each of the four dichotomies. Again, not in detail, but with respect to asymmetry, I say this is a unified approach based on extended factor graphs, but it lets you do things like rules and feed-forward neural networks, including with backpropagation, by restricting the messages that, that propagate through the original factor graph. And there's also reflection versus deliberation at the inconsistent level. Inconsistent, I won't explain associated version action rules, but a notion of knowledge versus problem space search, as is found in SOAR. Metadata, we have the metadata models as found in the common model, but structured here is lifted region tensors, which can be specialized in various ways. And non-combinatoric, you get things like reaction and deliberation, which are intended to be non-combinatoric versus reflection. Again, this is as in SOAR, tri-level control structure. Okay, conclusion on dichotomic maps. For dichotomies, you get a partitioning of the space of the underlying technologies, and key aspects of many of these dichotomies can be distilled down to just four. They drive criterial trade-offs, leading to the need essentially to span both ends of them. The maps then scope structure and relate the spaces of technologies to help understand combinations of architectural mechanisms, and even help more when you relate them to criterial trade-offs. I didn't really cover that much here. So the overall conclusion, we've got a hierarchy of analyses here, from computing as a whole through the relevant subdisciplines of AI and basically cognitive science, to an abstraction over cognitive architectures in terms of the common model, and ultimately to individual cognitive architectures. And we've looked a little bit at the Sigma architecture here. Each essentially contributes in its own way, with the hope that together they bring increased order and understanding to all these different levels, and ultimately aid in guiding new work. Thank you.